All right, guys. My name is Andrew,
And I'm Harold.
and we're going to show you our autonomous wheelchair project. Before we begin, I'd like to thank Dr. Woody, who's here watching live, but he's our project advisor, and he's helped us a lot throughout the semester.
So for our problem description for this project is why an autonomous wheelchair. So we want the project to be thought as, well, whenever you're walking, you don't think to walk, you just do the walking. So we want people that have limited movement with being a disability to feel the same way. So obviously right now people with wheelchairs have to manually move with their arms. That might require um, a more of a headache for them. So giving that sense of freedom back to them to not operate manually will give them that freedom to just navigate themselves with an autonomous wheelchair. So for our target market, for right now, we want to keep this project indoors only, just to limit the constraints and variables of the outside world. So our example, we're doing hospitals and nursing homes. So in the graph here, we have a nursing home situation. So it's low risk and you're maintaining control of the space environment that you're in. Um, the reason why this might be a target, well, is a target market is because sometimes you need to have nurses to wheel people around. That might be a little too complicated at times, depending on the time of day. So, for example, one situation we have, let's say you're at room 7 and you want to visit someone in room 1. Instead of having to call a nurse to wheel you over there, you could just use the wheelchair, pinpoint the address that you want to go to, and the wheelchair will take you there. Um, this would work for any bathroom situation, cafeteria, any of that sort to just travel around the building without having to have the obligation to ask someone else to move you. Again, you want to feel as free as we do walking around every day. So why just a prototype? So right here we have the prototype model. We brought it in.
Okay.
So it doesn't resemble a wheelchair right now, but we're keeping it as a prototype just because of the cost that it'll cost us to make. So us being a two-person group, our budget is only $200. If we were to actually implement an actual motor, battery, and a bigger chassis for an actual wheelchair, that would be more than double our current budget that we have. So the decreased size allows us to manipulate the complexity that we have, and it decreases the price immensely. So this chassis, we'll talk about our budget and the spending we did, but we're under budget. Keep in mind, only $200 to spend this whole 2 semesters.
All right. So first work we did was all in simulation. And so we also used ROS, like that first group, and we focused on RViz and Gazebo initially. And so RViz, there on the left, handles uh, the more nebulous aspects. So Gazebo on the right handles the physics simulation. So there you can see there's a little robot driving around a test environment. And so it handles collisions, joints, all that stuff. RViz on the right, it's robot visualizer. And so in the bottom left, you can see that's the perspective of the robot over there. And so RViz handles the mapping and the localization aspects. So we started by making a little model of our wheelchair, approximate size, and then we paired that with a model of the lab that we were working in. That way we could simulate the robot in that environment, and when we do the same thing in real life, we should get the similar result.
So moving on to hardware, our chassis is our wheelchair design. This was the picture taken of fall semester. Right here, we didn't have any camera implementation yet. We just wanted to focus that semester primarily on how we're going to move the robot and how we're going to communicate with the robot. At this process right here, at this progress, we had full keyboard control. This semester, our focus was to fully move to autonomous. Um, so our chassis is super lightweight. Keeping in mind our budget, we knew we were going to have smaller motors, so we don't want to put too much weight onto the chassis. Since during the semester, we'll talk a little more later about the first camera option we had. Due to that weight, the way the robot would turn, sometimes our turning wouldn't be as accurate. Whenever we took the camera off, the turning was much more accurate. We have two types of batteries on this robot. We have 4 AA's in the backside, and then underneath the chassis, we have a Pi power, which will power the Raspberry board on top and the Arduino board stuck in the middle right here that's upside down. And then the motor battery, the red board there, the motor controller will be powered by the AA batteries on the back side of the robot as well. So for our system layout, we have the Raspberry Pi, which runs ROS and Ubuntu on it. This would use the depth camera that we have for autonomy, and this will output the communications that the Arduino is communicating with the Raspberry Pi. We'll talk further about that. So what the Arduino does, it's the main communication for the motor controller board. So it'll take all the inputs and outputs of that board and translate it to the Raspberry Pi's output. Due to Arduino being coded in C and Raspberry Pi being in Python, we'll have to use pins to translate all of that language so it could simultaneously run under the Pi. And then right here's our motor controller. So these pins down here are our enable pins and our pins for the motor controller communications. This board is designed only to run 2 motors, but after doing research, we were able to see other people were utilizing the out 1 and 2s to combine 2 motors at once. So to save cost, we were able to do that with our motors as well. So instead of just having 1 motor on each side, we have 2 motors on the left and 2 on the right. So given the ability to run 4 motors, and then everything is wired through Arduino. And then this is just some sample code of our Arduino board. So this was earlier on fall semester on how we were going to move it for presentations coming up. This is the main way we communicated through Arduino to the motor controller. And then just to keep everything the same way, we'll show a schematic at the end, but our enable pins and our input pins all are the same color as you see there on the comments of the code. And then we also utilize case statements. So we have a case for forward, backwards, left, right, and stop. It just shows how the robot moves forward. So you have the left side runs fully high up, and then the right side motor runs fully high up. And then the other 2 are not running at all. So the motors would just spin at a forwards direction. And then the analog right, that's just the top speed of the motor at 255. That's outputting the 100% power for it. And then like mentioned before, there's our pin schematic. So it looks a little crazy here, but just to summarize it, the black wires are just everything grounded. And then the code that just showed all these color connections are just the wires connecting with each board independently to each other. And then our layout, so we have the Raspberry Pi on top, and then this board down here is what the Pi power is being connected through. You can't really see it, the battery is down here. There's just a wire that loops all the way up. And then the 2 boards in the middle of the Arduino and the motor controller. The reason why we decided to put the Arduino upside down rather than putting it on top, since we had space there, it's just because the wires, they weren't going to be too stressed. So keeping it close to what it's really going to communicate with, we wanted to keep that simplified so it doesn't have any problems in the future while running.
All right, next I'm going to cover the autonomous portion of our project. So powering it, we have a depth camera, and it was able to sense depth within 2.5 meters. And so that picture there is a picture of Harold and me on there to the left. So different from a regular camera, it does not capture images, well, not in the standard way. There's no color, no black and white. The colors there represent distance. And so the deep blue is so far that the depth camera doesn't know how far away whatever it's looking at is. And what you can see there is the gradual increase. The green Harold somewhere in the middle, and then the red and yellow kind of color is me closest to the camera. And we put that in with our SLAM algorithm. And the way this works is that, so the black represents the robot, and then you have the vision range of it. And so if you're turning it on there and it's looking at that wall, it creates a cost map. And so only what it can see is added to the map. And as it drives around, it's able to continuously build onto the map until it has mapped out in the entire environment. And the way we can localize with that map is based on weird edges. So if it detects that there's some kind of unique shape somewhere, or some other feature that stands out and is in only one place of building, then the robot can figure out that it's in that certain part of the building, and also its distance because we have the depth camera. So covering our results. Okay. There's, oh, there it is. Okay. Oh. Okay. So that was a video, but it was a video of us driving around our robot throughout the virtual lab room. And you can see it was fun to watch the little. It was almost like a mouse view of the room through that picture in the bottom left. Let's see. Is this one also going to? Yep. Okay. We also had a video of our robot driving around the room on a pre-programmed route, not fully autonomous, just to demonstrate that our hardware, our Raspberry Pi, outputting to the Arduino, outputting to the motor controller, all of that was working great. But let's have to imagine it. So another result is that we did run into some problems. So the first depth camera we had was generally too big, had put too much weight on the structure, and had unrealistic power constraints. And so we were thinking Big wanted to use depth camera and real cameras because that opens up more possibilities. It's more fail-safe, and you can also do more stuff with it. So if you wanted to use QR codes for localization as well, just so that if you wanted it to be able to ground itself at a location very easily, you have that option. But unfortunately, I broke it. So we moved on to a smaller camera, which you can see there is, I don't know, a 20th the size. And it also has power over USB, and it's lower resolution, maybe like 10 times less squared, of course. But it's still good enough for purposes that we're operating at and the small scale that we have here. And so now we're on the final state. We have our depth camera connected to our robot in the camera package, and we have the Raspberry Pi and the Arduino working, as you can see, well, with the robot driving around on its own. We're just working on getting the localization and mapping figured out in ROS, because it's not as easy as it would seem. But by May, we will have it all figured out.
So for our last part, we have the design management on how we came about this project. So similar to last group, last spring semester, we had a separate class, which is systems engineering. This is where we actually created our group on who was going to work on what. So for our realistic constraints, we have all of them here, but the notable two that we wanted to cover was health and safety and sustainability. Health and safety being that all safety measures, keeping in mind that an actual person is going to be sitting in this. It's not going to be a prototype at the end. It's going to be, hopefully, if this project continues, an actual person to be sitting here. So ensuring that safety measures are in place is very important for us. And then, especially for the customer as well. So then for sustainability, we want to have a way to have rechargeable batteries. Again, we were thinking of an actual wheelchair size model. So we want to have rechargeable batteries for like a station where you can just recharge your wheelchair rather than having to carry extra weight on board. and then also to be easy to replace for the customer. Again, we're keeping in mind that a lot of people aren't like tech savvy or they might have problems with technology. So we want to keep those restrictions minimal so it's easy for them to operate whenever they need it. And then for our standards here, we have three up here, and then two of the most important ones is the autonomous robotics ontology, which specifies the specific concept for autonomous robotic systems. So it just shows a way how autonomous robotics is represented. So we want to follow that standard as applied. And then for the second one that we were most implemented on this project was the visual content coding. So again, we're using RViz and Gazebo, which allows for a sort of a VR reality where we have it's all simulation, but we see it through a depth camera. So having that visual content for the user as well is important. And then this is kind of the graph of how we managed our time throughout both semesters. So there's kind of a downhill here just because one of us got sick, unfortunately. So, I mean, you got to plan for worse, as first group said. So, how we managed that, we just put more effort on the following weeks just to crunch down on the due time that we have. We do have deadlines that we had to reach. We also had a Gantt chart that we had just to meet those specific deadlines. So once we pass this hill, we realized that we were practically almost done the project. So we had a little bit of not relaxed time, but a little bit of downtime. But we kept our daily goal, our weekly goal of keeping the same hours. And then for our budget, this is how our budget is looking like. We're right at $200, so we made it right under the budget, which is pretty good. And then the way the budget was split up, we had to buy a new Raspberry Pi for this project. The Def Camera 1 being the Kinect, unfortunately, that broke on us. And then the wheelchair, the extra cables being just adapters of certain wires. And then the Def Camera 2 that we bought, I want to say probably 4 weeks ago. That's the tiny camera you saw in the earlier slides, bringing us at $198.72, right under the $200 mark. And then for our conclusion and future work, so to summarize this whole presentation, it's just to give a representation of a prototype using 3 specific boards for autonomous operation, and then also showing how cost-effective design allows for future development. So if future upcoming seniors want to tackle this challenge, they'll be able to see all the schematics, all the lab reports we have, all documentation would be provided. And then the main impact of this project was to enhance the mobility and independence for individuals with limited mobility. Again, the way I explained in the beginning is we don't think about walking. So we want that same way of thinking for these customers as well. And then this comes to play with improving accessibility and autonomy for them. And then for future work for the rest of the semester is just to implement better obstacle detection and navigation, just because we did run a little bit into problems with RViz where some of our packages aren't loading, but that's just trial and error at times. So with that future work, hopefully we get better readings, but I feel like by the end of by the end of the deadline, we should be good to go. So that being said, any questions?